So that's the housekeeping bit. And so to get going and give Steve all the time he can, I want to introduce Steve Tockey, our principal consultant here at Construx. He's been in the software industry for nearly 50 years, over half of those helping organizations improve their software development. He's the author of 2 books. You can actually find them still on Amazon. One is the low price of $131 a copy. I think you just snag them up. He would love to have the royalties. How to engineer software and return on software, which is really, really important for this particular topic, because the quality of service is really about the economics of that. Is like, how do we know how much of this to do? How much quality, if we use that term because it's in quotes here, should we have on something? And this is something that Steve has done a lot of work on. Not only has he written the books, but he was the co-editor and of many sections of the IEEE body of knowledge. Specifically, the one we care about is requirements. So tying in all that his economic knowledge and requirements is really in his wheelhouse. And with that, I hand it over to you, Steve, to enlighten us on the quality of service requirements, and then I'll debate you at the end.
Okay. Okay, thanks, Earl, for the introduction. Hello, everybody. And so let's just get started here. So economics of non-functional quality of service requirements. The whole goal here is to show how this category of requirements called quality of service requirements are best considered from an economic perspective. There's a number of problems with how they're being treated today on typical projects, and we can solve them by going at them from an economic direction. So the 3 basic topics today, I want to be sure everybody understands what I mean when I say a non-functional quality of service requirement. And then what we want to do is examine the economics, examine those kinds of requirements from an economic perspective, but one at a time in isolation. And then the last topic is to consider them all together at the same time. So individually, then as a group. So let's start off by talking about what a non-functional quality of service requirement is in the first place. And so Earl mentioned this IEEE Computer Society Software Engineering Body of Knowledge SWE/BOK Guide. And the requirements chapter in that. And SWE/BOK Guide is literally just a catalog of skills and knowledge that it would take somebody to be an industrial grade software professional. That's my elevator speech on that. Okay. And so there are different kinds of requirements. And we don't, I think, need to define specifically what a requirement is. I think for our purposes right today, we can just intuitively say that we understand what requirements are in general. Okay, but they break down into software project requirements and software product requirements, where the project requirements are constraints on the project. You have to finish in your budget is this. Don't spend over X amount of money. Don't take over Y amount of time, etc. So constraints on the project. The software product requirements are constraining the product. Okay, fine. The functional requirements are behavioral policies that the software needs to enforce, processes that it needs to carry out. If we're talking about an e-commerce system, the functional requirements would be around what does it mean to be a customer, what does it mean to be an order, what does it mean to proceed to checkout, what does it mean to cancel an order, etc. That's all functional. The non-functional requirements have to do with technology, and specifically the technology constraint flavor of requirements talk about named technologies. Write the code in C#, run in Amazon cloud, don't use pointers in a safety critical system. So they're naming a specific technology. Now, the focus of today, these quality of service constraints, they don't specify a named technology. It's not about a programming language. It's not about a database product. It's not about, again, some technology. It's about how well something needs to get done. I'm not telling you what technology to use. I'm telling you, the software people, that you need to make your technology choices in a way that get us this level of service, this quality of service. Now, There's an ISO standard, ISO IEC 25010, which is basically a catalog of the kind of things that typically fall under this quality of service kind of heading. Fault tolerance, accuracy, ease of use, time behaviors, performance, portability, adaptability, etc. And it's a whole big catalog of the kind of things that are typically important in this category. Now, one of the main problems that we see with these quality of service category of requirements is that they don't even get specified at all. And so it's up to the software team to guess how good it needs to be in terms of reliability, in terms of accuracy, and just basically we don't guess very accurately. And so part of the point here is that yes, there is this quality standard out there. You can incorporate that into your requirement solicitation activities and basically uses it as a checklist. I mean, hey, Mr. or Ms. Customer, do you care about accuracy of the output? If you do, tell me now. Do you care about fault tolerance? If you do, tell me now. Do you care about performance? If you do, tell me now. And so basically, this allows us to be more comprehensive, get a better set of these quality of service requirements, at least get them on the radar screen. Okay. Now, the next problem is that aside from them rarely even being specified at all, when they are specified, they're rarely quantified. The system shall be fast, the system shall be user friendly, but that doesn't help us. It really needs to be quantified. But then that leads to the other problem. If you're going to quantify it, as shown here for this mythical e-commerce system, the system shall support at least 500,000 customers. The system shall have a response time of 2.5 seconds or less. The mean time between failures shall be at least 2 weeks, and the mean time to repair shall be no more than 2 hours. That's fine. They are specified, they are quantified, but where did those quantifications come from? Where did the 500,000 customers come from? Where did the 2.5 seconds come from? And in my experience, that typically comes from the stakeholders basically saying, based on what I know I'm paying for this system, what do I feel justified in asking for? In other words, it's a rather arbitrary number. And the other point that it kind of brings up here is to ask the question, suppose I built the system in a way that only supported 999,999 customers. In other words, we didn't satisfy that quote requirement by just one customer. Does that mean that I failed? And I argue that not really. Okay. And so these are the kind of difficulties that we traditionally have. They're not specified, they're specified, but they're not quantified. They're quantified, but they're quantified very arbitrarily. And the whole point of today's discussion is that if we put on an economic perspective, that we can get them specified in a quantified way with understanding why the quantification is what it is. Okay. And so now we're going to shift over into looking at one at a time these quality of service requirements just individually from a financial, from an economic perspective. But just to be clear here, I'm going to start looking purely at a value perspective. I'll bring in the perspective of cost to deliver. I mean, because there's the value it provides, but then there's the cost that it costs us to deliver that value. I'll bring in the cost to deliver later. Right now, I'm just looking at the value side. Okay. And so the point here is that when I'm considering a particular quality of service requirement, maybe it's the number of customers that the system needs to support. Maybe it's the mean time between failures. I can quantify that level of performance as the measure of how much of that we're getting. 500,000 customers supported versus 400,000 versus 600,000. So the level of performance is how many customers are we talking about here? The value then for each of those levels of performance, there's a value that supporting that number of customers would bring to the stakeholders for whom we are building the software. And I think it's fairly obvious here that it should be a fairly linear ramp. As I'm capable of supporting more higher level of performance, in other words, we're supporting more customers, we have a longer mean time between failure, that brings more value to the customer in a linear way. If I were to double the number of customers, could I double the value to the customer, to the stakeholder? If I was able to double the mean time between failures, would that double the value to the customer? Well, maybe, maybe not. Okay. But the idea is that we've got this, hopefully over some range, a linear relationship where increasing the level of performance by some amount increases the value by a corresponding proportional amount. Okay. Okay, and so the idea of the requirement point, what are they asking for? What do they want? That requirement point just turns out to be one level of performance that should be somewhere on that linear curve. Okay. But now what I want to talk about is how I could economically justify that requirement point. And so for this mythical e-commerce system, suppose that we've done some analysis, and what we've determined is that, best of our knowledge, we think that the annual expenses of owning and operating such an e-commerce system are going to be $123,456,000. Okay, so we've estimated that. Maybe we've got some experience, but that's what it's going to cost us. Now, economically in our organization, if you pay attention to engineering economics, one of the things that they talk about is this minimum acceptable rate of return. And if you want to understand what minimum acceptable rates of returns are, get any good engineering economy book, such as chapter 10 of the Return on Software book. And so let's just say that the organization established that the minimum acceptable rate of return on projects in our organization is 15%. We need a 15% profit on every project, at least a 15% profit. Otherwise, we're not interested in it. Okay. So if you multiply the annual expenses by 1.15, then that gives you the 15% target annual revenue. And so in order to get that 15% acceptable rate of return, then our target annual revenue would need to be $141,974,000. Okay, fine. But if historically we know that we get an average annual revenue per customer is $375, then dividing the target annual revenue by the average annual revenue per customer says, well, the required number of customers to support is the 379,000 customers. Now I have an economic justification for that target. Okay, so that requirement point, remember, arbitrarily it was 500,000 before, but economically, really, it's just shy of 380,000. If we can support at least 380,000 customers, then that will allow us to achieve our minimum acceptable rate of return of 15%. So what we'll want to do then is repeat the same basic analysis. What is the expenses? What's the acceptable rate of return? What does that give us for the target annual revenue, which should be the same for all quality of service requirements. But then how does that level of performance affect the change in revenue? And basically run the math and say, well, in order to achieve the target annual revenue, then our level of performance with respect to that quality of service is X, whatever X is. And so that just for each one of those, mean time between failure, response time, number of customers, number of products supported in the catalog, whatever, each of them will now have an economically justified requirement point. Okay. So then the question is, if we assume a relatively linear ramp, I've never seen it not be linear, But the question is, as the level of performance increases beyond that requirement point, you go to infinity. As level of performance goes to infinity, does value go to infinity? As we go the other way, as we go, the level of performance decreases. Does value go to zero? And does it, and when? Okay. So that's the question I want to look at now. But for the starting point here, we want to look at the increasing level of performance. And so the idea here is that no, as the level of performance increases, value does not correspondingly continually increase. There's a maximum level of value that you're ever going to be able to achieve. And there are two reasons for this, okay? One of the reasons is that there could be, again, economic constraints on maximum value. There could be theoretical constraints on maximum value. I mean, and so if we look at, for example, something like social media, yeah, Facebook, for example, how many members does Facebook, what is the maximum number of potential members of Facebook? Well, it can't be any greater than the number of people there are on the planet, which is 7 point something billion people. And so even if Facebook could support 50 billion users, there aren't 50 billion people on the planet. So the capability could be there, but the capability doesn't bring value to the organization, Facebook, Meta, because there just aren't any more people to take advantage of it. So that's one reason why it's going to max out. The other reason that it max out is just basically not in this case, but physics. In order to get that level of performance, you have to exceed the speed of light, as an example. Okay. So either theoretical or practical limits say that you're going to top out at some maximum value, and the level of performance when you top out, that is what we're calling the perfection point. It's the most favorable level of performance beyond which there's no additional benefit. But again, I can approach this economically by saying, look, the target market, again, e-commerce, let's just say the entire target market of anybody on planet Earth who could potentially be interested in this kind of e-commerce, there's only 2.5 million of said people. But we also know, because there's competition in the marketplace, that we're never going to get more than 30% of that total market, which means that the maximum number of customers we would ever even conceivably need to support, 30% of the 2.5 million, that's 750,000. But again, at our average annual revenue per customer, if there were that many customers, our maximum annual revenue would be a little over $280 million, which is a healthy profit margin of 128%. Okay. And so now again, I just want to go through the same analysis. What is the maximum, the reasonable maximum in terms of the level of performance at which either you can't go beyond that level of performance because of speed of light and friction, or even if you could go beyond it, that's capacity that the stakeholders can't make use of because there aren't that many people on the planet or whatever. Just what level of performance yields maximum annual revenue in this particular dimension for this quality of service. Okay. Then do the opposite here, the fail point. What's the least favorable level of performance beyond which there's essentially no reduction in benefit? At what point have we hit rock bottom? Now, the idea here is we know that the annual expenses are this 123.5 million, and with the target, with the average annual revenue being $375 per person, that means that we need to, at a minimum, support 329,000 customers. Divide the annual expenses by the average annual revenue per customer, and that says, in order to even break even, then we have to have the 329 thousand customers. Okay, because if we can't support that many customers, we're not even going to break even. And so again, go through all of the relevant quality of service requirements individually, saying what level of performance gives me the minimum annual revenue just to break even, and that becomes that quote fail point. Okay, so moving ahead here is that we've now got a economically justified fail point, requirement point, and perfection point for an individual quality of service requirement. And in this case, we're talking about the supported number of customers, but we could do exactly the same analysis. We would simply have different numbers if we were looking at, for example, mean time between failure or number of products supported in the catalog or whatever. Okay. And so we've got the level of performance on the x-axis, we've got value to the customer on the y-axis, and we've got actual numbers in place. Oh, well, the fail point level of performance is about 330,000, which gives us no profit, no loss, but at least no loss, but no profit. The requirement point gives us our 15% minimum acceptable rate of return. And based on the 30% maximum market share, where the maximum market is 2.5 million customers, we're getting 128% profit if we can support 750,000 customers and we have that many actual customers. Okay, so this just being a concrete example of how those specific numbers lay out on this sort of lazy S-shaped curve. Okay, now sometimes the curve is sort of flipped 180 degrees. This is sort of top to bottom, if you will. Okay, sometimes increasing the level of performance decreases value. And the example here would be response time. Another example here would be the mean time to repair. As the response time of the system goes from 1/10 of a second to 2 seconds to 4 seconds to 6 seconds, the value gets decreased because the customer is spending more of their time waiting, and they're going to get bored. They're going to go to some other system, whatever. Okay. As the mean time to repair, oh yes, it did crash. If the mean time to repair goes from 2 hours to 2 days to 2 weeks to 2 months, clearly that's going to have an impact, a negative impact on value. But the important point here is basically taking the curve as we saw it before, where increased level of performance increases value. Here we're going to have an increase in the level of performance, decreases value. Less is better, but it will still top out at a maximum value, and it will still bottom out at some minimum value. It's just between we're sloping down, we're not sloping up. Okay. Now the important point is that just knowing what the requirement point turns out to be not nearly as useful as knowing what the requirement point is in relationship to the fail point, in relationship to the perfection point. So if all you told me was the requirement point was whatever it was, 379,000 customers, if that's all you told me, that really doesn't give me on my project enough information so that I know how to behave on the project. Okay. Because the idea here is when the requirement point is close to the fail point, let's just say requirement point is 379,000, fail point 329,000. That if my architect on my project comes to me and says, Steve, we've done all we can. Sorry, we're only going to be able to support 350,000 customers. What should we do about that? And, so the point here is, does the customer, the stakeholder, have the right to be upset? Sorry, Mr. or Ms. Stakeholder, you asked for 379, best we can do, 340, 350, whatever it was that I said. We're not meeting your requirement, but we're very, very close to the fail point. Oops. We got to be really careful here. Now, on the other hand, Suppose that chief architect comes to me and says, Steve, we've got this breakthrough. If we do this, we can double the level of performance. Instead of being 380, we go to 760. In other words, what I'm trying to get at is there's a tremendous upside here. Okay. If it doesn't cost that much to increase the level of performance, then I tell my chief architect, yeah, absolutely, go for it, because we can bring a huge amount of value, additional value to the stakeholders for not a huge increase in the cost of doing so. We don't have much room on the low side, but we've got a heck of a lot of room on the high side. Okay. Now, on the other hand, suppose the situation were somewhat reverse. The requirement point was 700,000, just making this up. Yes, requirement was 700,000, but the perfection was 750,000. In other words, we're very close to the perfection point, the requirement point, very close to the perfection point. Again, architect comes, sorry, Steve, we're not going to make 700,000. What's the best you can do? We can do about 675,000. Oh, okay. Does the customer have the right to be upset? Sorry, does the stakeholder have the right to be upset? And the answer is, well, yeah, because we're not meeting their expectation. But I would argue that they don't have the right to be very upset, because we're giving them the vast majority of the potential value that they were ever going to be able to get out of the system in the first place. Now, on the other hand, chief architect comes, oh, technical breakthrough. We could double the level of performance. We can go from 700,000 to 1.4 million. Should we do that? And the answer is, well, probably not, because that pushes the level of performance beyond the perfection point. There's not a lot of upside here. There's a lot of downside. There's not a lot of upside. And so that's kind of the whole point in this part of the discussion, is that it's not really enough to know what the requirement point is by itself. That it's much more helpful to understand what the requirement point is in relation to the fail point, in relation to the perfection point, because that tells me how much upside I have to overperform and how much downside I have, room on the downside, if we can't meet the required level of performance. Okay. Which then says, oh, well, maybe when we're specifying non-functional quality of service requirements, the specification should in fact be more descriptive. The system shall have an acceptable response time. Just don't say, oh, 2.5 seconds is what we're asking for. Be explicit and tell me what the fail point is. Be explicit and tell me what the perfection point is, so that I know what the relationship is between what I'm required and what the fail point and the perfection point is. Similarly, system shall have acceptable reliability. The fail point, mean time between failure, 1 day. Requirement point, 2 weeks. Perfection point, 1 month. What is the relationship of that requirement point to the fail point, to the perfection point? How much upside do I have? How much downside do I have? So that should I need to take advantage of the upside or the downside, I know how much of it is there. Okay. Now, if you do happen to be familiar with Tom Gilb's language, the planning language, then you're probably familiar with what he talks about in terms of scale, the unit of measure, which is what I would call the number, the quantification of the level of performance. The meter is the process or device that you're using to do the measure. Past, what have we gotten in the past? Trend, extrapolated future level, record, what's the sort of state of the art, what's the best we've ever done. What I'm really getting at here is that in language, he talks about survival, goal, and wish. Survival being the minimum necessary to avoid total system failure, which is analogous to the fail point. The goal is analogous to the requirement point here, and the wish is analogous to the perfection point. I would say that the only even marginally substantial difference between what Tom Gilb is saying and what I'm saying is that we're talking in the same terms. It's just that now I have an economic justification for why that value is, that level of performance is at the level of performance. that there would be some degree of potential arbitrariness if you worked everything in the language approach without considering truly the economics and the minimum acceptable rate of return and at what point do we stop making a profit, etc. So there's a high degree of correlation here. I'm just taking it a little step further and saying that I can justify the actual level of performance for survival, for goal, for wish from an economic perspective. Okay. But I'm going to say, let's take it even a step further. Instead of just telling me that here is the requirement, here's the fail point, here's the requirement point, here's the perfection point, tell me the value at the fail point, the requirement point, the perfection point. Okay, on the assumption that it's fairly linear value between the fail point and the perfection point, then you see that formula in red down across the bottom. The value at some given level of performance will be equal to the value at fail plus value at perfection minus value at fail. And what that's just doing is just scaling the value axis, if you will, the y-axis, the other half of the formula, the given level of performance minus the fail, and the given the level of performance at perfection. This is just basically figuring out the slope of that linear equation. Ultimately, that's all. So that if you give me some arbitrary level of performance, I can figure out what the value of that level of performance is. Okay. Given the best, given the worst, given the slope, you tell me where we are in the middle and I'll linearly interpolate what the value is. Okay. Okay. So up until now, we've only been looking at value, but what I want to bring in here is the idea of the cost to deliver. And the important point here is that I would argue that the cost to deliver is essentially going to be a step function. Look, it'll cost us this much, and for this much, we can support these levels of performance. Now, if you want to go beyond that level of performance, we have to spend more. We have to spend more to get better hardware, or we have to spend more to do something to the software, code optimization, whatever. Okay. And if we invest that amount, then that gives us the ability to go up to a new maximum level of performance. And if you want to go beyond that, we have to spend even more. And so that's why I'm showing this cost to deliver as basically being a step function. For all levels of performance between 0 and the A level of performance, it's going to cost us 122 million and a half to deliver that. Now, if you want to go beyond the A level of performance, if you spend more, 123,456,000, that will get you up to the B maximum. Now, if you want to go beyond B, you have to spend more, and that's going to be, so again, the idea of the step function here, which will now introduce the idea for an individual quality of service requirement, the most cost-effective level of performance being that level of performance that has the highest positive difference between the value at that level of performance and the cost to deliver at that level of performance, which we see as the B point right here. Okay, we have the highest value and the lowest cost, relatively speaking. We have the maximum difference, positive difference between the value and the cost. Okay, so now maybe all other things being equal, we should really be targeting that most cost-effective level of performance. That maybe should be our target point. Okay. And so this is one way of looking at it as the difference. Now, the other way of looking at it is what would happen if I took the value curve and I subtracted from the value curve the cost curve. And I looked at it in terms of the net value, not the total value, but the net value, which is the total value minus the cost to deliver. And that would be sort of this jagged sawtoothy example right here, where again, the most cost-effective level of performance is the highest point on that sawtoothy kind of picture. And all I did here was take the earlier value S curve and subtract from it the cost to deliver step function, and that's what gave me here. Okay. So now what we're going to do is transition away from looking at just an individual one at a time quality of service. So again, the number of customers that we allow, that we can support, the number of products that we'll allow in the catalog, the mean time between failure, the mean time to repair. Rather than looking at any one of those individually, now let's start to look at the whole collection of them all at the same time. Okay, so we're going into economics of multiple quality of service requirements, looking at groups, looking at the whole set of them as a collection. Okay, two things we need to worry about here. One of the things being what's called sensitivity analysis, and I'll go into this in a whole lot more detail in just a moment, which sort of sets the foundation, and then the overall system optimization is where we can start bringing in the idea of system engineering, engineering a system to give me the most cost-effective balance of all the level of performances. More on that in just a moment. So I'm going to start off by looking at the sensitivity analysis. Now, in this engineering economics, in this engineering economy field, sensitivity analysis is a kind of analysis where I have some function of some input, like level of performance, and some output value, and I'm looking at how much change to the input affects the output. If I change the input by this amount, how much does that change the output? A sensitive relationship would be little change to the input, big change to the output. An insensitive relationship would be one where we have big change to the input, really doesn't cause that much change to the output. Now, in order to do the sensitivity analysis, what we're going to do is one at a time. So we're kind of back to sort of temporarily looking at the quality of services requirements individually, but we're going to hold everything else at their required level of performance. And we're just going to take one out of that set, and we're going to change the level of performance from the fail point to the perfection point, asking the question, as we go between the fail level of performance and the perfection level of performance, how much does that change the value? And basically, we're just going to plot this. We want to make a graph. We want to plot the change in value on the y-axis as a function of the percent change in the level of performance on the x-axis. And so I just have to run a bunch of math to calculate a bunch of values so that I can plot the line. And then what I'm going to do, after having plotted all those lines on the graph, I'm going to find the quality of service requirements that have the highest slope, because they're the most significant drivers of value. And again, more on this in just a moment, okay? So while holding all of the other quality of service requirements at their required level of performance, if we only change the number of supported customers alone, then the fail point number of customers was, remember, 337,000. And the perfection point was about 715,000. Now let me just take steps between that fail point and the perfection point. What is that in terms of a percent change in the number of supported customers? And how does that change the value expressed in present worth? And what does that give me in terms of the percent change in present worth? So this is just a bunch of input data that says, look, if I held everything else at their requirement point, and I move the number of supported customers across its full range, its full dynamic range of levels of performance, then how does that change the value? Now I'm going to repeat that for holding everything else constant, but only changing the number of products in the catalog that we need to support. How many products can the customers choose from that are in our catalog? And I didn't show you the individual analysis, but the minimum number of products, the fail point number of products, is 875, and the perfection point is 2,900. But as we range across, everywhere between 875 and 2,900, how does a 10% change in the number of products supported in the catalog affect the value of the system? And now I have the data here. But then again, we were also talking about response time. The minimum response time, or the perfection response time was half. Oops, I may be in a little issue here. Okay, but if we assume that the perfection response time is half a second, the fail response time is 5 seconds. Again, all I'm going to do is vary response times between that fail point and that requirement point, seeing how that affects the value of the system to the stakeholders. And then what about the mean time to repair alone? Now I have a whole bunch of data that if I only change this thing between here and here, how does that affect value? If I only change that thing between there and there, how does it affect value? That's all the input data that I need. Now I'm going to plot that all on a graph. And this is really the sensitivity analysis. All of that was just calculating the inputs. This is now the output of the sensitivity analysis. What I'm looking for here are the lines with the high slope and the lines with the low slope. Okay, so mean time to repair and number of customers visually have higher slopes. Now, what that means is that those are the more sensitive. That's where I have more leverage in giving value to the stakeholders. The response time line is actually rather flat. The number of products line is actually rather flat. In other words, large changes in the number of products supported don't actually affect the value to the stakeholders that much. Relatively large changes in response time really don't change value to the stakeholders very much. There's not a lot of leverage there. I should not really need to pay attention to those because they don't bring much additional value. There's not a lot of leverage going on there. Whereas with the mean time to repair and the number of customers, it's like, oh goodness, I've got a lot of leverage here in terms of if I do well, big increase in value. If I don't do well, big decrease in value. I should pay more attention to how I'm doing with respect to the number of customers supported in the customer database and the mean time to repair. Okay. So then that I was just showing you sort of visually, but what I would want to do sort of more mathematically is calculate an actual slope. The sensitivity number here is the calculated slope. How much does the value to the stakeholder change for each 1% increase in the level of performance? And so the number that you're getting here is a dollar value change that comes with a 1% increase in the level of performance. That's the slope. And I've just organized them here in decreasing order of absolute value, meaning that the single most high leverage non-functional quality of service requirement that I have to deal with here is supported customers, and the least sensitive, the least leverage is in the supported products. Okay. And so if I can do the analysis visually, I'll just do it visually. But if I can't do it visually, then I have to do it mathematically is really the point here. And it just comes from calculating what the slope is. Okay. Now, this does set me up for being able to think about overall optimization of the system. Here's where I'm getting into system engineering. I want to find the optimum mix of values at level of performance to give the highest overall business value given the cost to deliver each. I'm trying to optimize a minimum investment for the highest value. Now, this would be trivial if I could hold each quality of service requirement at its most cost-effective level of performance, as we talked about before. If I could just put each one of them at its most cost-effective, then this would be simple. The unfortunate side of this is that there's conflict between these kind of requirements, in the sense of if I want to make the system more efficient, I can make it more efficient, but the things that I do to make it more efficient will tend to make it less maintainable. There's sort of cross feed here. I can make the code more portable, but the things that I do to make the code more portable will make it less efficient. So higher portability decreases efficiency, but higher efficiency decreases maintainability and also decreases portability. So there's some feedback loops going on here. And the point is that the sensitivity analysis that we did before will then guide us into questioning about the kind of trade-offs that we can or should be making. Okay, would the stakeholder be willing to trade worse number of supported products for better performance in the number of customers? Okay, would they be willing to trade? Hopefully you can see the pointer on the screen here. Would they be willing to suffer from a small decrease here in order to have a big increase here? And the answer is probably yes, because it doesn't reduce much value in terms of number of products, but if I can take that capacity and push it over to the number of customers, then I get a high upside leverage for a relatively low downside cost. That's a kind of trade-off that now it's an intelligent trade-off. It makes sense. And the same idea here with would they be potentially willing to trade some small hit in response time? Maybe they're even willing to take a large hit in response time because it's not very sensitive, if it would, for example, give them an increased benefit in the mean time to repair or the number of customers supported. And so it's just, oh, now I know where my leverage are. Now I know the things that are the higher leverage, and I can and should potentially be trading things that are low leverage to get high leverage benefit. Okay, don't bother trades that involve response time and supported products because those are low leverage things anyway. Okay, so let me wrap it up here, leave some time for questions. That we talked about what these non-functional quality of service requirements are in the first place, and they are the, if you will, the illities: reliability, maintainability, but then you have accuracy, usability, whatever, okay? And typically they're not specified at all. If they are specified, they're not quantified. The system shall be fast, the system shall be user-friendly. If they are specified and they are quantified, the quantification is usually fairly arbitrary. And so by bringing in this economic perspective, we can quantify them in a systematic and meaningful way. Individually, what's the required level of performance? What's the perfection level of performance? What's the fail level of performance? And then we can look at them with the sensitivity analysis as a collection and start thinking about trade-offs and be in a position to negotiate with the business stakeholder and say, you know, we could actually give you more value if you were willing to change that requirement point from there to there. And if you change that requirement point from there to there, we could actually give you a whole lot more value out the back end by trading things that are not that valuable to you in exchange for things that really are valuable to you. Okay, so these non-functional quality service requirements, they don't constrain to specific name technology. I didn't tell you what programming language, I didn't tell you what database, I didn't tell you what CPU, I didn't tell you to use any particular name technology, but I did specify some level of performance, some quality. I need this many customers supported. I need this mean time between failure. I need this mean time to repair. I need that quality of service, okay? As I said, these are often not even considered, partly, I claim, because they're so hard to deal with if you're not dealing with them economically. But if you deal with them from an economic perspective, it reveals a much deeper, richer understanding at an individual level, at a collective level, making them much more manageable, much more understandable, and much more reasonable to deal with. Okay. And so again, my goal here was to talk about how these non-functional quality of service requirements are best considered from an economic perspective. If you wanted to track down the references, if you noticed in the lower left-hand corner of the slides, it referenced Tom Gilb's competitive engineering book, for example, Sweebot Guide, and a couple other things. So there you go. Okay. This is not my own work. If you go get the written paper, and again, the written paper we'll give you a link in the YouTube description. The paper was co-written with a consultant friend of mine, Jianyang Zhang. Here's my background, here's her background, and the paper was a joint effort between the two of us. Okay. So with that, let me kick it over to Earl and see if there are any questions from the vast listening audience.
Well, we do have questions, Steve, and it's been kicked up, but let's throw a couple softballs at you, hopefully real quick, and then we'll get into some bigger ones. We had one question is basically what happens if your two big leverage ones or your handful of leverage ones are in conflict? That is, increasing one negatively impacts one of the other high leverage ones. Is there a strategy for dealing with that, or is that just like, oh, you got a nasty trade-off, pick which one has the better value?
Yeah, I mean, it really just becomes a nasty trade-off, and let's talk to the stakeholders and say, here's the nasty trade-off. Are you happy with how that trade-off is sitting now, or would you? But now it's exposed. Everybody understands that it's going to be a nasty trade-off. Whereas, up until now, if you weren't looking at them from an economic perspective, you could be unknowingly making very nasty trade-offs and having a huge impact on your stakeholder without even knowing that you're in the middle of a nasty trade-off.
Yeah. And on a similar token, what if I can move two needles with the same budget dollar? That is, I can increase one of my quality of service areas and another one, but I'm not spending different money. Is that just like a happy coincidence, or should I factor that in saying, well, I can get two for the price of one here, where the other one I'm spending the same dollars and I'm only moving one needle?
Yeah, I mean, just understand that spending the $1 may not only affect one of the levels of performance or one quality of service. The spending the $1 could in fact affect multiple levels of service. If I buy a higher performance database, it's going to give me the ability to support more customers and more products in the catalog. And so just understand it's not a one for one. I could, two birds with one stone kind of deal. Yeah.
It seems to me like an added benefit, a lot easier problem, better problem to have. If I was trying to make a case for a particular solution, I could say, look, we're moving these three needles with this dollar investment. A dollar investment over here is only moving this one needle or one place on the thing. Right. So we think the better investment would be over here moving three for that same dollar.
Yeah. But the other side of it, now just quick thinking here is, again, the sensitivity. Maybe spending the $1 moves the needle much farther in this one than it does in that one. So I really want to pay attention to the one where it moves the needle farther.
And in the sensitivity graph where everything crossed at the one point, that's just the zero value point, right? Which is the common to your data set.
It's the point at which it shows me the value if all of the levels of performance are at their required point.
The required point.
Yes.
That's the 0%. And so if we increase it by 10% or decrease it by 10%, what's the difference? The 0% is the current stated requirement point.
Right. So if you take all of those quality of service requirements and you hold them all at their stated requirement point, then what is the value of the system to the stakeholder when everything is at its required point? And what we're saying here is what happens when you move off of that required point for that one quality of service requirement. Which way do you go and how quickly do you move up or down?
And the interdependencies between these things. I mean, we're looking at each one independent in this graph, but there could be a thing saying, hey, our response time, changing that actually drives up the number of customers, right? Are we just getting too far into the weeds worrying about it's like, well, if the number of products actually impacts the number of customers, because if I have more products, more customers will come. Or is that just an argument we have to make when we're presenting this as our potential solution?
Well, okay, but be sure that we understand what the context here is. I mean, because the computer has a limited capacity, then I only have so much space in my database for products in the catalog. And because the computer has a limited amount of capacity, I only have enough space in my database for some limited number of customers. I can't have infinite products. I can't have infinite customers. Okay. And so it's not that more products gives me more customers. What I'm saying here is I need to have the ability to support this many customers, because if my database is not sized to give me that number of customers, then I can't get that value, because I can't support the customers because my database isn't big enough. So
and value, we were just talking about ROI, or are we talking about just pure revenue?
Well, in the end, it has to be. In the end, it has to be net profit. In the end,
net profit,
where I'm balancing the value that I'm getting with the higher level of performance against the cost of delivering that level of performance. And so, while the analysis was kind of sitting at just looking purely at value of no, we really do need to consider the cost, where the value side, the pure value side, is linear, and the cost to deliver is the step function. Yeah.
Step function. Yeah. Yeah. And are you also worried about a payback period for that value? I mean, you could say, yes, it gives us that value, but it's going to pay us back. We'll earn that value over a course of 5 years, 1 year. Is that a consideration about time in this idea of value?
And yes, and I snuck that one in on you. Okay. It may not have been obvious. I was using the present worth at an interest rate over some time horizon. So this might have been a 7-year study period. It might have been a 10-year study period. It might have been whatever that study period is. I'm looking at a present worth given that minimum acceptable rate of return. So let me just say that, yes, it's important to consider the time frame, but the nature of the analysis that I did makes that consideration implicit. I kind of snuck it in on you.
Yeah.
That if you are familiar with engineering economy, present worth is for a cash flow stream over a time period at an interest rate.
Right. We have time for just a couple more questions here, I think. Some of the areas in ISO 25010, particularly things like security. When people think security, they usually think certain technologies. They're going back to that technology, that stack. What would potentially be the unit on a security that we would do sensitivity analysis on?
That would be an excellent Tom Gilb question, because Tom would say everything is quantifiable.
Right.
And I agree with him.
I've actually got an answer to that I use. It depends on your business, like number of records lost, number of breaches per decade, breaches per century.
Well, breaches per unit.
What's the bad thing we're trying to avoid?
Well, breaches per unit time, and for every time there is a breach, what is the damage done by the breach?
Right, and we take a medium breach of size X, or we can even do a staggered one where we have small breach, medium breach, extravagant breach.
Yeah.
Right? And different cost factors, and really make that up. But the trick with something like security is you can't measure it in the technology. You have to find that unit that your business cares about over a period of some time.
Yeah.
Right. Because, especially like you said, mean time to repair. Because one of the things that I think a lot of people struggle with, if they ask their customer, what do you want? Well, I want instant mean time to repair. I want all the security. Why don't I not want it all? That seems to make sense to me.
I want it to be perfect.
What you're really making an argument for is what are you willing to pay for?
Well, yes. Let me be a little bit more clear here. It's uh, beyond the perfection point. It's not giving you any value. Okay. Maybe you want to support an infinite number of customers in
Yeah,
your
but even on
customer
that
database.
slope, right? That step function says, if you want to pay for more, the step function says, if you don't want to pay a lot more for this, right? You sure
Mhm.
you want the perfection point, but you're only willing to pay at a level
Right. And
in terms
so,
of money and time to deliver, because getting from A to B may take another 7 months of development time. Well, I got a
right.
trade show to hit.
Yeah. And I actually engineered this particular picture on purpose by saying, interesting that the perfection point is somewhere around here, right?
Yeah,
But the cost to deliver at the perfection point is higher than the value at the perfection point.
perfection point.
So
So
even if
you're not going to
you,
do that.
yeah, I mean, even if you wanted to be there, it's going to cost you more than you can afford to be there. So sorry, that's kind of silly.
All right. Well, we've used up the hour, folks, and we went a little bit over. I want to thank everyone for attending today. If we didn't get to your questions, I'm sorry about that. But Steve is happy to interact with you and answer specific questions. There was a real interesting one of people with doing some stuff with metrics. But you can drop us a line at comments@construx.com, and I will make sure that gets to Steve, or you can write to Steve directly. I think on your end slide, Steve, do you have your email address as well? You can pop that one up.
Should
Usually
be.
you're
Yeah.
supposed to. Yeah, there it is. Steve
Steve
T
T
at
at
construx.com.
constructs.com. Mm-hmm.
Yep. Right.
Just
So you can
fire me
drop
an
him a
email and
line.
we'll have
And
a conversation.
yep, he loves to do that. So, Steve, thank you very much. I think this has been an excellent presentation, and I look forward to hearing from all the people attending. Look at all the hands clapping. we'll we'll hopefully see you at the next webinar soon. Goodbye, everyone.
Okay, thanks, Earl. Goodbye, everyone.